So, good afternoon. Closing session, closing lecture of the summer school. And you're all still here, so very good. Yeah. Um, I think we have seen some very good, but also very intense lectures. So I hope you still have a little bit of space left in your brain to digest some more information. Um, well, it's a good thing they put the best presentation for last. So happy about that. You don't agree, Victor? No. Yeah. Okay. My name is Paul van Beurden. I'm with Tata Steel in the Netherlands, indeed. I lead a research team at Research and Development. And I will be taking you along on our company's journey of becoming a green steel producer. And I will talk about how refractories and digitalization help us with that. Who of you has been to Tata Steel once? Yes. Okay, that's quite a lot. Very good. Good for you. So for those who haven't been to Tata Steel yet, I will introduce our company very shortly, very briefly, and then continue my story. So, yeah, it's a bit difficult to see. There's a bit of a greenish glow from this projector, which makes my presentation even greener, but it also makes it a bit more difficult to see the map. Well, basically, Tata Steel is a global company. We have production sites mainly in Asia and in Europe. And in Europe, I have a pointer, yes. We're in the Netherlands and in the UK at Port Talbot. We're around 70,000 people working at Tata Steel. We produce around 30 million tons of steel annually. Well, from now on, I will focus on Tata Steel in the Netherlands mainly. And yeah, just to tell a little bit of what we do. So we produce steel for a wide range of markets, running up from packaging to automotive and consumer products like washing machines, etc. Also battery steels, for instance, that is in the packaging part. All the premium suppliers of batteries like Duracell, they use our steel. And as a fun fact, who of you is carrying some of these euro coins around? Yeah, Victor, yeah, very good. Well, Ivan already mentioned it in his presentation, but actually these coins are copper-coated steel coins, steel made by Tata Steel. So congratulations to those who are having these coins with them or on them. You're carrying a little bit of our steel around. So just a fun fact. It's not a big market for us, as you can understand, but it's a nice thing to tell all with. Okay, green steel transformation. We have two programs in place. One is really focusing on the local environment, emissions, odor, etc. I'm not going to tell about that today. The other part is going green steel production. And we're doing it in two phases. First, in 2030, we will replace one of our blast furnaces. We have two in IJmuiden by a DRI, DRP, a DRI producing plant, and an electric arc furnace. And in 2035, we will install the next one. Ah, yes. Hello, guys. Okay, yeah, I think most of you are familiar with it, but I will just briefly mention it. So we're an integrated steel site, that meaning from the raw materials up to the coil. The steel coil can be galvanized or painted. Most of the CO2 is produced right here at the blast furnace. You all know this equation. This is the only equation I will show, so don't worry. So this will be, the blast furnaces will be replaced. I said we do that in two phases. The first phase is, so we have the coking plants and blast furnaces. One coking plant and blast furnace is replaced by a DRP and an EAF. And in the second phase, we will introduce another DRP, and we go to different type of melting furnace. It's not definite, not fully determined yet how that will be looking. Okay, so the first phase. These installations will be phased out and replaced by a DRP and an electric arc furnace. Looks very simple in this way, but it is not. It needs to be integrated upstream and downstream. There are quite some challenges there. Not going to address too much about it. This is the first phase. And for those of you who have been at our site, you probably have had a tour in the Bosch plant. That's just what you see here. And this is all going to be new, going to be built here. The DRP, and this is the electric arc furnace. So this is how our site will look in 2030. It's a huge transformation. Okay. Steelmaking. So this is how we do it now, schematically. Raw materials, blast furnace, of which we have two. Hot metal is produced, transported to the Bosch plant. And with primary steel making and secondary steel making, and finally cast it into a slab. So the first step is to replace the blast furnace and with electric arc furnace that produces steel. So you can skip the conversion, the primary steel making, and then further integrate it in our production process. And in the second phase, as said, we're aiming at a different way of producing steel. DRP, but then a reducing electric furnace, sort of a submerged arc furnace, well known in all kind of alloying metal production. But that's producing hot metal. And we do that because then we can make different steel grades so to cover our current portfolio. So still, then we do still need to have to do the primary processing, primary steel making. Okay, let's zoom out a bit. We've heard a lot about electrification, hydrogen. But it's easier said than done. To set the scene, this is the global steel production. Around 2 billion tons per year. And as you see, the vast majority is produced in China. Yeah, it's enormous. This is the part, the other curves. If you zoom in, if you leave out China, you also see that India is increasing and Europe slightly decreasing. So that's currently the situation. Energy, green energy. This is how much electricity we currently produce. The green and the blue part, so that's renewables and hydro and nuclear, which we call for now green. And the gray parts is coal and gas and fossils. 30,000 terawatts hour is produced. 24 was produced 24. 40% almost was green. And we produce, as said, around 2 billion, 1.8 billion tons of steel. If we go green, then we need, it's estimated around 4 megawatt hours. That means 50 to 100 terawatt hours of green steel. In other words, 43% of all the green steel produced nowadays needs to be, is necessary for the entire steel industry to go green. So we don't produce enough green energy and green electricity by far. So we can say we want to produce green steel, but that cannot happen without producing more green electricity. Okay, sort of a summary. There are quite some barriers. This is started by Shell, the oil company. Green energy, that's a challenge. Then there's regulations that needs to be in place. if you only go green and local, only in Europe, for instance, and not globally, that also puts offsets the market. So these are challenges. We need to have some kind of regulations and incentives. Especially for the EAF, we need higher grade ores to be able to still make the same quality of steel. Of course, assets, skilled labor, that's a challenge. And financing, we don't have a lot of margins on our steel. So if you go green, margins are under pressure. But that's definitely an opportunity. Customers, they definitely want green steel. So they ask us, make green steel, and we're willing to pay more. So all in all, balancing everything, we will get there. We're quite confident about that. Energy prices, last thing I will say about this. Energy prices in the Netherlands, just one regular day, you see the prices are very volatile. So you can imagine if you need large amounts of electricity, small differences in price have a huge impact. As said, currently we're self-sustaining with respect to energy. Mostly it's coming from gases as a side product from our raw material production, raw material treatments. But we need more electricity when we go green, and we don't have our raw material. We don't use cokes anymore, so we enter the market. So we definitely need to optimize how we produce steel and when we produce steel, depending on the prices. So modeling, optimizing the electricity prices, focusing on the demand, the production will be very important. Okay, that was the bigger picture. We go green, but we also need to be more energy efficient. Because we cannot, just by using hydrogen, we don't fix everything. There's more CO2 produced. As you remember, as I said, especially in the beginning, 60 to 70% of CO2 reduction, where we go to the new technologies, the new way of steel making, but still there's a gap to reach 100%. This is a picture from the World Steel Association showing the CO2 effectiveness of all the steel industries in the world. On the steel industries that use a blast furnace. As you see, we're second here. The first, we're not sure it is. It's anonymous. It's probably a very modern steel plant in China. So in Europe, we're probably the most CO2 efficient steel producer in the world, but not in the world, in Europe. But what you also see, if you look at this axis, this is the amount of CO2 produced per amount of steel. You see that it's a factor of 2 or something. So basically, the steel industry is rather a CO2 producing industry with steel as a byproduct. So let that sink in. It's enormous. Okay, goal for energy efficiency. So why is it so energy intense? Well, high temperatures is the basic answer. We have the raw material preparations. We have the blast furnace operating at over 2000 degrees centigrade. The Bosch plant, 1600 degrees. Hot strip mill, cold strip mill, etc. A lot of energy intense processes. Okay. Well, we can optimize a lot, but we'll focus on part of the project chain. This is the blast furnace. And we have the second one is a torpedo car transporting the hot metal, as I mentioned, to the steel plant. And the rest of the presentation will focus on the torpedo car and on the steel plant, especially the steel ladle. Okay, energy efficiency, the steel ladle. How can we use or benefit from refractories to improve the energy efficiency of the steel ladle? Well, here's the torpedo, just to put it into perspective. And the steel plant is in the Bosch plant, both in the new as in the current situation, with the purple arrows pointing at a steel ladle. For those who don't know. So the steel ladle at Tata steel. It's about 5 meters high. Contains about 340 tons of steel. Temperature around 1600. And a refractory lining. Most of you know this, but for those who don't, and well, you have seen it now. Okay, a little bit more about refractory lining. As Olivier also pointed out, every plant has its own philosophy on what is the best lining. Well, we have the best lining, obviously. This is a schematic, how it's built up. We have a working lining, a wear lining, in contact with the steel. It's a fired spinel brick. Good resistance against heat and steel. But also high thermal conductivity, so not very energy efficiency. Very energy efficient. Safety lining, bit less resistance, bit higher thermal conductivity, and so on. And here are two insulation linings. And of course, the steel is not very, steel shell is not very insulating at all. Yeah, this is then how it looks. So this is a microporous layer, safety lining, sorry, insulation lining, safety lining. And here's the spinel brick working lining. Okay, so how do we evaluate the thermal balance, the thermal efficiency of a steel ladle? Well, we also make colorful pictures for our directors, as you see. But we don't do that with CFD, but with finite element modeling. And we always validate our models with experimental measurement data. So we put in thermocouples in our installations and yeah, measure the steel ladle in this case, also torpedo. Actually, this is a torpedo lining, so I'm tricking you a bit, to validate the fab models. Because you want to have good validated models because rubbish in is rubbish out, garbage in is garbage out, as Victor pointed out. Yeah, so here you see the lines are the thermocouple measurements, and the fab model are the squares. So we have quite experienced, I think, for decades we make these kind of finite element models. So we're quite confident that we can really simulate or represent a steel ladle with such models. Okay, you might remember we have also a production site in Port Talbot, and they have a different lining. Of course, it's worse than ours. And you lose temperature of the steel between the converter and the casting. And Port Talbot loses around 10 degrees more during this process than we do in similar conditions. So 10 degrees, is that a lot on 1600 degrees in total? Well, yes, it is. 1 degree centigrade of steel its value is around, say, €500,000 per year. I'm not going to go into the details, but so you're throwing away millions of euros if you just don't have your thermal management under control. So you can save a lot of money by just optimizing steel ladle or managing your operation better. Okay, reminder, it's simplified working lining and insulation lining, the build-up of a steel ladle in this case. So what happens? Steel ladle contains steel, 1600 degrees, loses heat through the lining, right? And this is the R is the thermal resistance of the working lining in Port Talbot and in IJmuiden, and this is the thermal resistance of the insulation lining of Port Talbot and IJmuiden. So obviously, what you see, thermal resistance at Port Talbot is lower. Okay, so we understand when we lose more heat, right? Seems very simple. Okay, so how are we going to fix this? Well, we put in more insulation, right? Okay, so we put in the same insulation, and it's a nice thing of models. You can explore scenarios without experiment without actually doing it, and you will see indeed, yeah, we lose less. Okay. Now let's put in more insulation because we're gonna want to catch up with IJmuiden. 200. Indeed, it gets higher. But wait. 225. Total resistance of the lining is over 200. IJmuiden is around 150. But still, we lose more. Why? Well, actually, the answer is not that difficult. It's only unless you change the working lining, lower thermal resistance, but then you catch up. So why is that important where you put the insulation value? Well, because a ladle is, at least half of the time, it's empty. So when it's empty, it radiates a lot of heat. So what happens, when it's full, it heats up. When it's empty, it cools down. And if you look closely, actually, what you see is that the difference, that the temperature difference is in the working lining, not so much in the insulation lining. So you can put in as much insulation as you want, but it won't improve your energy efficiency of the ladle. So you should be looking at the working lining. Thermal breathing. Or you can put a lid on it and it's empty. Also a simple solution. Okay. So what does this show? It's just an example, but I think it shows how important real refractory engineering, understanding the mechanism is to be able to improve. Energy efficiency is not a matter of just putting in more insulation or very, very sophisticated insulation materials. So the suppliers of insulation materials, probably among you, yeah, it's very important, but it's not the entire solution. It's a combined solution. It's the entire lining that determines the energy efficiency. So, and it seems a simple insulation, just a steel ladle, but it is not, yeah, when it comes to energy efficiency. And that, can you imagine a blast furnace much more complicated? So thermal modeling is how we discover this. So if you wouldn't have done that, we would have just put in more insulation and go. Pay more for the materials and go. That wouldn't have helped us. The thermal model is a vital tool for value use at a total cost of ownership, also addressed by Olivier. Don't look at the price of the materials only, but look at the total picture. Okay, next topic. Energy efficiency of insulation. We've just discussed, and now we're going to look at the process itself. And we're using AI for that. Okay, remember, so again, the scheme, the current situation, but also in the new situation, we still have these transport vessel, the torpedo, which was the second topic I was going to talk about, as I said. Well, this is a torpedo, for those who haven't seen one yet. Cigar-shaped vessel, around 30 meters, something, transporting the hot metal from the blast furnace to the steel plant. Contains around 400 tons of hot metal, around 1500 degrees. And as with all installations, it has a refractory lining. And that refractory lining determines the temperature behavior, just with the steel ladle. Okay, we have some challenges there. Hot metal losses. So that's just yield losses that is related to the hot metal temperature. I'm not going to explain why, but so you want high hot metal temperature to have less yield losses. Circularity. One of the pictures of the production scheme, you saw that, or maybe I didn't point it out, so you may have missed it, but what we do is we put in the BOF vessel or hot metal, but we add scrap to it. Scrap is cheap and it increases circularity. So you want to put in as much scrap in your BOF vessel as possible. But if you put too much, you cool down the hot metal too much, and you freeze your process. So you don't want that. So the higher you can deliver your hot metal to your BOF vessel, the better. And there's something to do with the steel grade quality, why you want higher temperature, but also I'm not going to address that here now. So we need a tool to be able to keep the temperature up, so to be able to manage the logistics of the torpedo itself. Okay, so we have around 20 torpedoes in our site, so that's quite a challenge. So what we do, we develop the finite element models, the beautiful pictures, but we can't use them in real time. A finite element model simulates a scenario of a torpedo, but it takes hours to get to an answer. So you can't use that real time, and operators can't use it. That's useless. So we need to derive some kind of what we call reduced order models, which run real time. And we derive them from our FEM models. They're also validated using measurements, so they contain experimental information, but also modeling information. Why do you use models to generate data for your reduced order models? Because with models you can calculate scenarios which do not happen in reality or are close to failure, scenarios which hardly happen ever. So to increase your data set, we use models. Well, these models, these reduced order models, we can combine into a digital environment, a digital twin, which we then can use for the operators to optimize the process. And if we then also put an artificial intelligence agent who can provide decision support to our operators, we can more or less automatically get the best management of your torpedoes. And the management of torpedoes, I will explain what I mean with that here. So we have a blast furnace, steel plant. Torpedo is filled at the blast furnace with hot metal and delivers that hot metal to the boss plant, and it's empty. It also has a buffering function. The blast furnace process is not in sync with the boss plant process, so a torpedo is used also as a buffer to have a continuous operation. When a torpedo is full, hot metal inside cools down, and the torpedo itself, the refractory lining, heats up. When the torpedo is empty, the torpedo cools down. And then there's different times. Every torpedo has its own ride. For several reasons, it can be longer or shorter. And it has its own age. With that we mean how many cycles it has done, how many heats. The more heats it has done, the more it wears, so the different it responds to temperature. So every torpedo is unique in that sense. And we have 20 running around. Well, take the best torpedo from all of them to lose the least temperature. That's quite something you cannot solve. Okay, back to our colorful pictures. Just a bit of steel ladle. We also have a finite element model of the torpedo, validated against temperature measurements. And I said we cannot use a FEM model to optimize, so we need a reduced order model. Unfortunately, it's a sort of machine learning technology behind it. Unfortunately, it was explained before by Victor and also by Ivan, so I can skip that part. So what we do, we calculate a lot of scenarios, simulated a lot of scenarios with FEM, so offline, to generate this database. Using indeed a machine learning technology, we built a reduced order model from this. And actually it's performing very well. It's one too big, one too fast. So what usually takes 2 hours for a FEM model to calculate, we can do the same with such a reduced order model in 1 second. Okay, don't mind too much the pictures. Basically, we have 3 reduced order models. I mentioned just before, hot metal cools down, torpedo heats up, or when the torpedo is empty, it also cools down. These are 3 temperature equations, basically, which we capture in the reduced order model. So no further details there. Okay, then the big picture. The reduced order models. Based on finite element models, which are in turn validated by experiments. We put that in a digital environment. We can also put in sensors, GPS sensors, for instance, to track the torpedoes. And we can couple that to a artificial intelligence agent, a reinforcement learning agent. So what this does, this agent, from all the 20 torpedoes we've running around, it takes one torpedo to be filled, for instance. Then using the reduced order model, it's calculated what's the temperature effect. And there's a final result. And if the temperature effect is good, if you lose a little bit of energy, it gets rewarded. If it's a bad choice, then it gets penalized. So in that way, the agent learns. And you can put it in a nice digital environment for the operators to manage the torpedoes. Okay. Needs to be here. Let's see. So let's start. Yeah. So on the left, this is a simplified version, one blast furnace, 10 torpedoes. Each torpedo is different with their own temperature behavior and its own temperature history. And right-hand side, it's not about the details, just walk you through. What happens there, let's use the pointer. What we put here are the temperature, hot metal temperature loss from one torpedo between the blast furnace and the blast plant. First in, first out. That's what FIFO means. If you just take the torpedo that's available, that's what we currently do. The operator see a torpedo, come on, you go. Let's fill her up. Or if you use, in this case, is customized heuristic. So there's not AI. This is just mathematical optimization. If you just optimize mathematically, you already save a little bit of energy. So yes, there's room for optimization. So, oh, seen that. This picture is again first in, first out. This time it's in gray. Customized heuristic, orange, and here I have plotted the reinforcement learning. So what happens? This is the hot metal temperature, not the loss, the hot metal temperature, so the higher the better. The reinforcement learning and the first in, first out and the customized heuristic, they all start the same. And the reinforcement learning agent doesn't know anything, it just follows the first in, first out, and then starts to learn. So in the beginning, there's no difference, but then at a certain point, you see, especially the first in, first out, you see some torpedoes which lose a lot of temperature. And the reinforcement learning and customized heuristic are more or less similar. The customized heuristic is just a little bit better here, but the reinforcement learning agent is really learning. And as you continue, at some point, especially here, you see reinforcement learning starts to perform better. There can be some scenarios that the customized heuristic has avoided to use cold torpedoes, for instance, but at some point it only has cold torpedoes to choose from, so it loses energy anyway. But reinforcement learning management, the reinforcement learning agent manages to avoid that situation, so it's outperforming the customized heuristic. Okay, so what does the operator see? Well, this is what we're currently developing, or heading to a demo phase where we're going to implement this. The gray lines are the tracks. Here are the blast furnaces, and here's the boss plant. And the colored bars, these are the torpedoes. The left-hand side, you see the metrics for every torpedo, the steel grade, the temperature, how much hot metal it contains. This is actually from real life data. And then we can actually simulate and later on also optimize to provide decision support to the operators. And just to say, take that torpedo instead of that, because then you save so much temperature, it's so much CO2, it's so much money, whatever you want. Want to gamify it a bit, to operators to compete against each other, to make the most money and to lose as little temperature as possible. Okay, it is quite a novel approach. I haven't seen other steel companies doing this. So combining digitalization and physics-based simulation. Reduced order models, very important. Real-time modeling with accuracy of high-fidelity models. We can generate them from FEM models. You can put them in a digital twin for real process simulation. Actually add a AI agent to it to optimize the process itself. So with that, I conclude the presentation. Digitalization is the key. Is going to be the key. Is the key for a sustainable and profitable business, steel business, but basically any business. Okay, that's it. I see that the industrials are very good at timekeeping. So that's it. Yeah. Yeah.
Yeah. Thanks, Paul. Thanks a lot for this interesting talk and insight of your work, how to be energy efficient. Yeah, open for questions. Yeah, there is, was earlier. Sorry.
Yeah.
Was faster.
Thank you. Very nice presentation. Two questions. Because I'm also in the steel industry. Still, everyone is steel industry. Yeah.
Yeah.
Sorry. So
just get it.
yeah, one question is this: in your stage 2 level, and if you are introducing REF, and we know that the carbon in the REF will be much lower than in the blast furnace. So then, are you also expecting to change the BOF, actually the refractory, mild carbon refractory? That's my first question.
Yeah.
And the second question is, you are tracking this torpedo car now, but how about the ladle? Are you also tracking the ladle in the similar way? Because that's also very important, especially for the casting is related directly. And that actually the ladle temperature.
Yeah, excellent questions. Indeed, when we go to the REF electric furnace, most likely the converter lining needs to be changed. In fact, going to the EAF, the steel ladle lining also needs to be changed. So although we have the best lining for the old-fashioned way of producing steel, we need to go to a new lining as well with the EAF. Yeah. So I put it very simple. Just replace the blast furnace and the coke plant, and you're done. But that's not true. No, there's a lot of changes downstream, especially as well. And for your second question, yeah, the ladles. Yes, we also have done a similar thing. We're experimenting with the hot metal ladles, and also the steel ladle is in scope for this as well. Yeah, yeah. This is a demo phase still. So it's but as soon as this works and kicks off, then we want to roll out this to the rest of the production chain. Yeah. 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 Welcome.
Just one more question.
Yes.
Sure. Congratulations, Paul, for the presentation.
Thanks,
and congratulations for Tata Steel Netherlands. Knowing from inside what the steel company looks like and the future of the steel company, opening your heart, what would you advise the refractory industry for the future?
That's a very good question. I'm trying to evade the political minefield. No, I'm kidding. I need to give that, but yeah, the steel. What will be a challenge is the startup phase. So when we have the new installations in place, the EAF will run. It will be bigger than anywhere in the world. So that's new, never done before. Same for the DRP. Also, when we introduce extra hydrogen, so startup phase will undoubtedly be accompanied with a lot of maintenance, a lot of shutdowns, incidents, etc. So what we would want from our refractory suppliers is that the refractories will perform indeed under these new conditions. So they need to understand the process very, very well, talk to us as well. We have these models, we have this information, and together we need to make sure that installations will not continuously fail and fail and fail. Don't rely on all linings, but think in terms of the new process. Don't stick to things you already know. It has always worked for years. No, this is new. This is different.
Thank you.
Yeah, thank you. Yes, thanks again, Paul. I mean, you showed, I mean, you don't have as a steel producer, not all facts in your hand. I mean, there are some things around you, and the whole industry and this area is facing this, for instance, energy prices. But I think you gave a very good example how engineering helps, I think, really to come even faster to better solutions and, of course, yeah, to the commitment we had. Thanks again for this. All right.